welcome to the next lecture. So, today we are going to talk about work and heat. First of all, we will discuss what is work. So, we all know that work is, so you know what is work? Work is force into displacement, right. Force is a vector, displacement is a vector, and we can write work as the dot product of force and displacement. So, now if I write that, expand that, it will be modulus of the force, modulus of the displacement and cos theta, which means that we have done several times this kind of problems, where there is a mass m and then the force is pulling in this direction, force is pulling in this direction, sorry, and the displacement is in this direction L, and the work done will be depending on the angle theta, right. We have done that kind of problems, mass in a slanted direction and all that. However, in the type of thermodynamical work that we are going to consider here, typically we will consider a box full of gas molecules and a mass m sitting on top of that. Now, when a mass m is sitting on top of a piston, so this is the piston, then the force that is acting on the gas is on this direction, and that force is typically mg, mass multiplied by the gravitational attraction g. Now, there can be two different situations, one is compression, another is expansion. So, in case of expansion, the length, let us say the area is fixed, for a fixed area, the length of the or the height of the gas molecules is going to increase, right. Let us say I draw that here. So, now since that happens, which indicates that the displacement is in the opposite direction of the force. What is the theta there when there is expansion? Theta is no in the expansion case, theta is 180 degree, right. So, since theta is 180 degree, your work done will be minus f, when I am not giving any vector sign, which means I am just taking the modulus f into L, right, which is in that case. Now, let us say, okay, I will leave it here. For compression, however, what is happening is, in case of compression, your force is acting on that direction and your displacement is also along that direction. So, theta is 0 degree. So, work is just F L. So, you see, in case of compression, the work is positive. I will say positive. In case of expansion, work is negative. You just note down that, we will come back to that. Now, since we are writing work as F into L, F by A into L, I am just dividing and multiplying with A. F by A we know to be pressure, A L will be the volume, surface area into length will be the volume. So, you see work done is basically for gas systems is nothing but P V, but in case of expansion it will be minus P V, and in case of compression it is plus P V. And that is a very important point that is often confusing in thermodynamic classes, that when one takes the work to be positive and when the work is to be negative. But we have to consider by convention that we always consider work is done on the system. So, we have to see what is the work done on the system, okay. That is what we always take as a convention. So, conventionally, therefore, when we do a compression, then in case of compression there is a positive work done on the system, and in case of expansion it is a negative work done on the system. So, you see that in case of expansion, the gas molecule is doing the work, system is doing the work. So, system is doing a positive work. Therefore, oppositely conversely work done on the system is negative. Have you got that, this particular part? So, because the gas molecule is expanding, so gas molecules is pushing the piston up, pushing the mass up. So, it is doing the work, it is doing a positive work, therefore, the work done on the system is negative. Similarly, if you see the compression, now here we are doing work, the mass is doing work on the gas and it is a positive one. So, if you see, we have to always take conventionally work done on the system, because if you do that you will see that whenever the work done on the system is positive, the internal energy of the system will increase. So, therefore, we will always equate internal energy to work done by taking work done on the system. So, let us see, yeah. So, we have talked about that, we always calculate work done on the system. Okay. Now, this is PV work, however, there can be other kinds of work also. So, PV work is like hydrostatic work, and then there are other kinds of work also. So, let us say if in case of a bubble, when the bubble becomes bigger and bigger, so it is actually working against the surface area, because there is a surface tension associated with that. So, as the surface area increases, it requires more and more work. Elongation, so when we have, let us say we take a rubber band of length L and we try to extend it. So, that is a work that is done, and that the force multiplied by the length which we discussed will be a kind of work of elongation work. And another work is electrical work, where the charge is carried over electric potential, and that will give rise to some kind of work. So, there are different kinds of work, but we will consider mainly a PV kind of work in this particular course. So, for a very small amount of changes, when the work is done on the system, so what will be the sign then? So, let us say we have a mass m, right, mg. So, you see that if we have by convention, if you take work done on the system always and that to be positive, then we can write that as dW as minus P external dV. So, it is how much the external mass is doing the work on the gas. Work done on the system means how much the mass is doing the work on the gas, right. So, it is the pressure exerted by the mass, which means the external pressure, that is under consideration. So, right now when the system is in equilibrium, your internal pressure and external pressure are equal, they are balanced. However, let us say that point we can consider as here. So, let us say it is a PV diagram and initial pressure is P1, volume is V1, when there is a mass m sitting there. Now, let us say suddenly we are going to change the system to M2. So, whenever we change the system to M2, so here the pressure was mg, let us say that was P1 equal to mg, and here the pressure is M2g. What is going to happen? Now, let us say when we change at t equal to 0, we just replace m by M2, suddenly there is an imbalance between the internal pressure and external pressure at t equal to 0. Internal pressure is still mg, but external pressure is now M2g. So, what will happen now? The system will start to go to an equilibrium. Now, initially, so that the pressure here, the gas molecules here will try to adjust and there will be lot of turmoil. So, this is called typically the non-equilibrium situation, which thermodynamics does not care. What thermodynamics cares is that if we wait long enough, let us say we call it that t equal to infinity, but we do not need practically an infinite time. We wait long enough, then what is going to happen is the internal pressure is now going to be in equilibrium with the external pressure, okay, and it will adapt correspondingly a different volume. Let us call that as P2 and V2. What happened in between this and this we do not know. We only know the initial point and the final point. Remember always that thermodynamics does not tell you what happens in between. Thermodynamics only tells you one equilibrium point to another equilibrium point only, and also it does not care about the time that it takes to go to that equilibrium point. It may take 10 seconds or a million years. Ultimately, what we are going to see is that one equilibrium point to the next equilibrium point. So, that is why we do not know what is there in between, but given the information of P1 V1 and P2 V2, we can calculate certain properties. First property is that internal energy U, that is independent of how we do that, independent of the process, which means that given this initial and final point, we will know that what is the change or difference between the internal energy of the initial point and final point. However, do you think that the work done will be same every time when you go from state 1 to state 2? Okay, let us do that through some example. Okay, so let us see. Yeah. So, this is what we talked about. So, here there was 3 masses, we suddenly changed to 2 and then we got at different states. Okay. Now, how do we calculate the work going from state 1 to state 2? How do we calculate that? And each point in the PV diagram, so each point in the PV diagram is a state, right. The state is defined by these 2 points. For one component system, 1 molar one component system, if we specify 2 variables, that is enough to specify the system, because which means that if we know PV, we know the T automatically for n equal to 1 molar. So, since we know that, we will specify the system with a P1 and no with 2 values P and V, and we will get the internal energy for that. But however, work done will strictly depend on how we do that. So, for example, let us take this particular problem in which our initial point, let us say, is this one, where the pressure is 2 P 0, it is not exactly 2 P 0, but let us call it 2 P 0, and then volume is V 0. So, our initial state 1 is characterized by 2 P 0 pressure and V 0 volume. Our final point is here, which is characterized by P 0 pressure and 2 V 0 volume. It will be just opposite, volume will increase because pressure is decreasing. Now, in order to go from state 1 to state 2, either we can take this route or we can take this route. Let us call that route number 1 or path number 1, and let us call that path number 2, and let us calculate the work done for path number 1. So, work done, now how do we define work done? So, remember we already we discussed that work done is basically PV. Now, if I do dW, which means should it be PdV plus VdP? Do you think it should be like that? Except there is a one problem here. The problem is that you see, when I say VdP, that means I am allowing the pressure to change. But imagine what was the situation? The situation was that I had mass m with the gas and I suddenly change it at T equal to 0. T equal to 0 means I can actually replace it, I can cut it and put mass m2, okay. And then I wait some time, let us say T equal to infinity, and then I get a different system where my m2 is there and my volume has changed. So, this is my P1 V1 and this is my P2 V2. Now, did the pressure change? Because see, our system that we talked about was m2 in the beginning at T equal to 0 and m2 at the end. That did not change. What changed was only the volume, because based on the external pressure the volume got adjusted. therefore, the dP is 0. Okay. And since we are always talking about work done against the external pressure, we have this minus P dV, because you see if the volume increases, it is a positive quantity, then work done on the system will be negative, and expansion is a negative one. If volume decreases, dV will be negative term and negative will be positive. So, compression will give you a positive work done. So, the formula for work done is minus P dV. Okay. Now, since we know that work done is minus P dV, but external dV, that is also another important point, because the system is now adjusting with the external pressure. So, either you can think of the system or the external pressure doing the work, whatever you can think of. Ultimately, this is the formula that we are going to use always, P external dV. Now, let us see for the root number 1. So, it goes from 2 P 0 at 2 P 0, because pressure is remaining constant, but volume changes from V 0 to 2 V 0, right. So, what is the work done in that step, in first step, can you tell me? P external is 2 minus 2 P 0 into 2 V 0 minus V 0, right. In the next step, you see the external pressure, you know, can you tell me how much is the external pressure in the next step? Step means from here to here. In this step, what is the external pressure? Imagine that finally it is equilibrating to that pressure, whatever the external pressure you did at t equal to 0, at the t equal to infinity also that pressure is remaining. So, you have to always consider the final pressure that you are going to see in the system. So, in the next step, what is the pressure that you are going to take? P naught, correct, minus P naught, but volume did not change. So, 2 V 0 minus 2 V 0, which means that is 0. So, this is 0 and the first one is giving you minus 2 P 0 V 0, that is the work done in the root number 1. What is the work done in root number 2? First step is final pressure is P 0, right. So, minus P 0 into volume did not change, and that was V 0 minus V 0, and the second step external pressure is P 0, right, and volume change from V 0 to 2 V 0. So, this gives you 0, it gives you minus P 0 V 0. So, you see in two different routes, by two different routes or two different paths, going from same point, same fixed point to another fixed point, you are getting different work done. Okay. So,
why have we taken the final pressure?
Yes. So, as I explained to you that let us say, so the question is that why you are taking final pressure. I will explain that once more. Let us say I start with a mass m and the system we call that as state 1, okay. And I am going to a state where the mass is, let us say, m 2. Here the volume was V 1, here the volume is V 2. Okay. I can take mass of m 1 V 1, m 2 V 2. Okay. So, that means our P 1 is m 1 g and our P 2 is m 2 g. Okay. So, now how did we do this particular operation? Although this is an equilibrated system, correct, this is also an equilibrated system. So, these are two equilibrated systems, but when we try to do that at t equal to 0, we have changed the mass from m 1 to m 2 at t equal to 0 and then allowed the system to go to equilibrium. So, that means the system did work against this external pressure, because at this external pressure there was no work, system was perfectly balanced, the internal pressure and the external pressure was perfectly balanced. In this case, however, the internal pressure and external pressure is not balanced, and that is why the work was done. So, that means the system, the gas molecule expanded against m 2 g and came here. and see this is our final pressure. So, that is why we are taking the final pressure for the calculation. Is it clear? So, that means what we say is that we say that work is path dependent. Now, how does the system will do the work? The system will do the work because in order to do the work, you know how it has to go from one step to another step, right. So, let us say if you do not supply anything, any heat or anything, so when it is expanding, your internal energy has to decrease, right, because the particles are separating from each other. That is why we talked about real gases and all, right. You saw that when the particles are going apart from each other, your energies were increasing, right. So, interactions were decreasing. So, and when there is getting compressed, then the other thing were happening, right. So, in an adiabatic process, or you can say that in case of isolated system, when there is no heat input or output is allowed, then the system is using its internal energy to do the work. And we can write that delta U, that means change in the internal energy, is equal to the work done on the system, not by the system. If you do work on the system, then your internal energy will increase, right. You compress the gas, your system internal energy will increase. You expand the gas, internal energy will decrease. So, that is why work done on the system. So, whenever we write work, that means it is inherently assumed that it is work done on the system, and that will increase the internal energy of the system. So, because we are not supplying any other thing. So, when a process happens, it has to happen through some energy, it has to spend something. So, that is what it spends. So, that is the first part.